Good evening, everyone, and warm welcome to the third day of the Cosmic Chronicles webinar series presented by SEDS Mora. We believe you all enjoyed the previous sessions and are just as eager as we are for today's captivating topic. It is my great pleasure to introduce our esteemed speaker today, Ms. Vishadi Liyanage, who is currently in her final year completing her degree program in Bachelor of Science Honours in Physics at the University of Rouen. She has cultivated a deep interest in astronomy, driven by a passion for uncovering the mysteries of the universe. Her academic journey has been enriched by her research in her final year work and during her internship at the Arthur C. Clarke Institute's Astronomy Division, where she contributed to cutting edge research in understanding astronomical phenomena. With a strong foundation in both theoretical and practical aspects of physics, she has demonstrated an unwavering commitment to understanding the vast cosmos and sharing that knowledge with others. In addition to her academic endeavors, she is the president of the Physics Society at the University of Rouen, a role that reflects her dedication to fostering a collaborative learning environment and inspiring others. It is with great honor that I welcome Ms. Vishadi Liyanage, President of the Physics Society at University of Rouen, today's session. Today's session of Cosmic Chronicles, titled An Introduction to Optical Telescopes. She will guide you through the fascinating world of optical telescopes, uncovering how they work, their role in astronomical discoveries, and how they have helped us unlock the mysteries of the universe. Additionally, we have arranged a short Q&A session with Ms. Mishadi after her presentation, where you will have the chance to engage in discussions and clarify any questions you may have. If you have a keen interest in astronomy and are looking for guidance or seeking advice on the right path to follow, this would be a great opportunity to connect with her. So, without further delay, I invite Ms. Vishadi Liyanage to commence today's session.
Good evening, everyone. Thank you for that beautiful introduction, and thank you for having me for today's session. As I was told, this is the third session that you guys are having. So I think this is a really good initiative because in our basic degree, most of the students do not get the opportunity to learn astronomy. But there are so many students with the passion towards astronomy. So I think this is a really good initiative, and I'm really grateful to be joining to this session today. So I'll share my screen. Please let me know if you can see it. So I assume that you can see my screen and you can hear me clearly.
Yes, we can see your screen.
Thank you. Okay. So today we are going to talk about the optical telescopes. So here's a brief overview of the contents that I'll be sharing with you guys today. So first of all, I'll give a brief introduction into what telescopes are. Even though our major focus is optical telescopes, I think it's important to talk a little bit about what telescopes in general. And then I'll move to talk about varieties of telescopes. And then we'll move to our major focus, the optical telescopes part. And after that, I'll classify the optical telescopes based on their design and the aperture size. So we'll discuss in detail what these terms are, these aperture size and all that. So next, I'll briefly talk about the components that these optical telescopes are made of. And after that, I'll move to the large optical telescopes part. We'll discuss a little bit about the large optical telescopes as well. And finally, before concluding, I'll talk about some telescope stats that we need to know when we're using an optical telescope. So first of all, let's see what a telescope is. As you guys know, as everybody knows, a telescope is something that we use to observe celestial objects, right? In specific cases, we use telescopes to observe ground-based objects as well. But most of the time, in a typical case, we use telescopes to observe celestial bodies. So what a telescope does is it basically gathers or collects light or electromagnetic radiation that comes from celestial objects, and then it has the ability to magnify these electromagnetic radiation. So there are a few types of telescopes based on the region of the electromagnetic spectrum that it can detect. So we'll look into those types in the next slide. So as you can see, the optical telescopes are in the first picture. So there are so many different types of optical telescopes. So the picture that you can in the picture that you can see, it's a fixed telescope. So what an optical telescope is, it can detect visible light rays. So we are going to discuss about optical telescopes in detail in the upcoming slides. And then if I move to talk a little bit about the infrared telescopes. So I think you all have seen this telescope. This is very popular because this is doing a great job giving incredible images of the deep space to the Earth at this moment. So this is the James Webb Space Telescope. So this is in the infrared category. So as you can see, it has gold coating in the telescope mirrors. So that's why it can detect the IR rays specifically, and it can also detect red and orange rays in the visible band as well. And then you can see these radio telescopes. So you can see they have this huge dish-like antenna. So using that, it can actually detect the radio waves. So there's a benefit in using these radio telescopes. So when the sky is cloudy, we cannot do observations using optical telescopes, right? But it's not an obstruction for the radio telescopes. And then there are a few other types like IACT telescopes, X-ray, and ultraviolet. So actually these IACT telescopes, IACT means the Imaging Atmospheric Cherenkov telescopes. So what these telescopes do is they can detect the high energy gamma rays that come from the celestial objects. And then we have the X-ray telescopes. So as you can see, the X-ray telescopes and the UV or the ultraviolet telescopes are in space. They're located in space, right? So there's a reason for that. Actually, these X-ray telescopes are located in space because our Earth's atmosphere absorbs the X-rays that come from celestial bodies. So that's why they have to be located in space. And when it comes to ultraviolet telescopes, it is also located in space because, as we all know, our Earth's atmosphere block the UV rays, right? So yeah, somebody has mentioned that it's James Webb. Very good. So we'll move. Okay, so here we come to our major focus, optical telescopes. So I briefly explained about optical telescopes in the previous slide as well. So what these instruments do is they gather only the visible light, right? That's why they're called optical telescope. So they can gather or collect the visible light using the primary mirror, and then it can magnify so that we can see the celestial objects clearly. So what can these optical telescopes do? So they can actually increase the resolving power of the images, and they can magnify the objects. So we are going to talk about this resolving power and magnification and all these terms later in detail. So here in this image, you can see some different types of telescopes, optical telescopes, that are, this image is from the Arthur C. Clarke Astronomy Division. So they have a lot of optical telescopes. So here I'm going to classify the optical telescopes. So you can see that there are three major categories: refractors, reflectors, and catadioptric telescopes. I think it's very important to know about these categories before using a telescope. So if we talk about the refractor telescopes, they have lenses as their optical element in the telescope. And in the reflector telescope, they have mirrors as the optical element. And when it comes to catadioptric telescopes, they use both the mirrors and the lenses in the optical design. And then if we divide the refractor telescopes once again, we can see there are two major categories. We can identify terrestrial and astronomical telescopes under the refractor telescopes. So what terrestrial telescopes are, if we look into what terrestrial telescopes are, they're used to observe ground-based objects. So most of the time we use the telescopes to observe celestial bodies, right? But in specific cases, we use these terrestrial telescopes to observe ground-based objects. And when we talk about astronomical telescopes, it can again be divided into two categories: Keplerian and Galilean. So the difference between Keplerian and Galilean is in the optical design. So in Galilean, we use a convex lens and a concave lens, but in Keplerian, we use two convex lenses. And if you talk about the reflector telescopes, we have Newtonian, Cassegrain, and prime focus telescopes as major categories. So the difference between these telescope types are also in the optical design. So specifically, if I talk about this prime focus telescope, typically we use a camera instead of using our naked eye to do the observations using the prime focus telescope. And then when it comes to catadioptric telescopes, which is the hybrid one, where we use lenses and mirrors. So we can see two major categories: Schmidt-Cassegrain and the Maksutov-Cassegrain. So the difference between these two types is in the corrector lens. So there's something called the corrector lens inside these telescopes. And in the Maksutov-Cassegrain telescope, the corrector lens is quite somewhat bigger than in Schmidt-Cassegrain design. So here I'm going to talk in detail about the refractor telescopes. So in the first image, you can see a refractor telescope that is in Arthur C. Clarke Institute. So here you can see how the light rays work. So this is how the light rays travel inside the telescope in refractor telescopes. So here you can see the primary lens and the secondary lens. And if we move to talk about the reflector telescopes, the first one is an image of the reflector telescope. This is a Newtonian type reflector telescope. And this is how the light travels inside this optical design. So you can see the primary mirror and the secondary mirror, which is a diagonal secondary mirror. And then it focuses, it redirects the light towards the eyepiece. Can somebody confirm if these simulations are clear? Can you see them?
Yes.
Thank you very much. So then we move to the catadioptric design. So you can see how the light travels inside the catadioptric telescope. So there's a hole in the primary mirror in the catadioptric design because this is a Cassegrain type. And then it focuses light towards the secondary mirror, and then it redirects the light toward the focuser. And as you can see in this image, we place our eye here, and we can do the observations using the catadioptric telescopes that way. And now I'm going to classify these telescopes, the optical telescopes, once again, based on the aperture size. So we can identify several types. So we identify an optical telescope as a small optical telescope if the aperture size is less than 4 inches. And we call it as a medium-sized optical telescope if the aperture size is 4 to 8 inches. I think I explained a little bit about what aperture is, but I'll explain once again. We are going to talk about apertures in detail in the coming slides. But basically what aperture is, the diameter of the primary mirror or the lens of the telescope. So we can identify 8 to 16-inch aperture telescopes as large telescopes, and the telescopes that have an aperture size more than 16 inches, we can identify them as very large telescopes. So in very large telescopes, you can see there are multiple lenses, right? Or mirrors. So up to 16 inches, we can use a single mirror in our design, but after 16 inches, we can use a combination of mirrors because it's very hard to build telescopes mirrors that are bigger than 16 inches. So they use a mirror combination in here. And in this dashed line, you can see the effective mirror size, effective aperture size. And when it comes to giant telescopes, giant optical telescopes, we consider 8 meters and above aperture telescopes as giant telescopes. So maybe you can see this aperture is made of a lot of small hexagonal shaped mirrors. So we will talk about these giant telescopes in the upcoming slides as well. So here, maybe you can see the size of a tennis court in here. Let me show you. Okay, this is the size of a tennis court, and this is the size of a basketball court. So if we compare with this scale, you can see how big these telescope mirrors are when it comes to this extremely large telescope or giant Magellan telescope. So some of these telescopes are still in construction level, but you can see in the other image, the size of a primary mirror of the very large telescope compared to the size of a human, right? So I'll stop my screen sharing for a second, and I'll try to show you an image of the extremely large telescope. Can you see my screen?
Yes, yes.
Yes, thank you. So this is the extremely large telescope. You can, if you go to this website, you can see how this works. And this is the Giant Magellan Telescope. So when you go to their website and scroll down, you can see all those details. You can see how powerful the design is. So when we compare the sizes, so this is the size of a blue whale, and this is the size of a space shuttle, and how you can see how big the Giant Magellan Telescope is. So I'll share my presentation once again. So I hope you can see the screen once again. And now we're moving to talk about the components of a small and medium-sized telescope. So we can identify two major parts when it comes to a small or a medium-sized telescope. The first one is the optical tube assembly. We also call it as OTA. And the second one is the telescope mount. I'm sure that you have seen these two parts in a telescope. So what an OTA is, we can identify as the housing of the telescope. So it holds all the optical elements inside this OTA. And the mount is the thing, the part that holds the OTA. And it also assists in pointing to a celestial object when we are doing the observation. And then I'll talk about the OTA components in detail. So you can see some images of the mirrors. So we have a primary mirror in the first image, and a secondary mirror in the second image. And we have a lens. And basically these primary mirror cell and the secondary mirror holder are the holders for the primary mirror and the secondary mirror of the telescope. And in the last image, you can see the focuser. This is where light gathers after redirecting from the secondary mirror. And then you can see some more components of the optical tube assembly. So we have eyepieces, Barlow lenses, a diagonal, and finder scopes. So if we talk about the sequence of how these components are connected to the optical telescope is, actually we connect the focuser that we saw in the previous slide to the optical tube, and then we can connect the diagonal. In some cases, we can use a Barlow lens, but it is optional. We don't have to use a Barlow lens all the time. And if we do use a Barlow lens, we can connect the eyepiece to the Barlow lens. Otherwise, we can connect the eyepiece directly to the diagonal if we're using a diagonal. And then we can see these two types of finder scopes. So basically, the difference between these two finder scopes is in red dot finder, there's a laser dot that point to the celestial object that we are observing in the sky. So what these do is actually the optical finder scope is like a small telescope. But the thing is, it has a less magnification and a more and a higher field of view. So the problem is when we observe through a telescope, sometimes it's hard to understand where we're looking at. Because through a telescope, the field of view of the sky that we can see is very narrow. So sometimes we are confused. We cannot figure out where we are looking at. So in such cases, we can use these finder scopes. So before using a telescope, we have to use a finder scope. To do this, like we can fine tune the telescope using these finder scopes. And we can do that by like focusing to object in the ground, like a distant ground-based object. We can use a distant ground-based object and do this alignment, and then we can use the telescope. So now I'm going to talk a little bit about the telescope mounts. So there are two major types of telescope mounts that we can identify. So the first one is altitude azimuth mount, and the second one is the equatorial mount. So in the first diagram, we can see what an altitude azimuth mount looks like. So there are two different axis movements in the altitude azimuth mount. And when it comes to equatorial mount, there are three different axis movements. So I think if I show a video, you can understand this better. So in this simulation, you can see how the altitude azimuth mount works. So I'll play it once again. So you can see the altitude movement and the azimuth movement of the telescope in this simulation. So these two axes are the azimuth and the altitude. And now I'll show you how the equatorial mounts work. So as you can see, first, like before using equatorial mounts, we have to align that. We have to point that to the North Star. Like the altitude we have to set before using the telescope, and that altitude changes based on your location. Like if you take an example, if you're in Colombo, it's about 7 degrees. So we have to do that adjustment alignment before using the equatorial mounts. As you can see, it's pointed towards the north celestial point. I'll play that again. So here I'm going to further talk about these altitude azimuth mounts. So as you can see, there are three major types. So the first one is Dobsonian mount. So if you are new to astronomy observations, you can use this mount because it's not very expensive, so you can use this one. And there are two other types called double time fork mount and single time fork mount. So like we can use single time fork mounts for telescopes smaller than 10 inches. So for the telescopes bigger than 10-inch aperture telescopes, we can use the double time fork mount. And these mounts, some of these mounts also have automatic tracking systems as well. So what they do is when we give the time and the location, they can track, they can automatically track. Like if we give a name of a celestial object, they can track and find that object when they have these computerized automatic tracking systems. And these are two types of equatorial mounts. So the first one is German equatorial, and the second one is fork equatorial mount. I'm not going to talk about these mounts in detail. So in German equatorial mount, you can see there's a weight. So you have to balance this weight with the weight of the telescope before using the telescope. And now I'll move to talk about large optical telescopes. So you can see an image of the James Webb Space Telescope here. But actually we cannot categorize James Webb Telescope as an optical telescope, because I think in the previous slides I mentioned that it has a gold coating, and it can detect IR, infrared radiation. And it can actually detect red and orange radiations as well in the visible spectrum. But mostly we identify it as an infrared telescope. So if you talk a little bit about what these large optical telescopes are, why they're designed. So these are designed to collect more light, because sometimes we cannot see fainter objects that are so far away. It's really hard to observe these objects using the normal telescopes that we have, the small or the medium-sized telescopes. So for those observations, we have to use these large optical telescopes. So these telescopes, as you can see, have a very large aperture. They use big mirrors and lenses to collect more light. And they also have a higher resolution. So we will talk in detail about these resolving power and all that in the coming slides. So here you can see some of the large telescopes that are available in the world. So this in the first image, you can see Grand Telescopio Canarias. Also we call it as GTC, and it's located in Spain. And we also have Keck Observatory, which is located in Hawaii. And then we have the Very Large Telescope. We previously saw the primary mirror of this telescope. We also call it as VLT, and it is located in Chile. As you can see, we choose deserts most of the time when we are building this type of large optical telescopes. The reason for that is the less light pollution, because in the cities, when it comes to cities, the light is highly polluted, and we cannot do successful observations. So we use deserts when building this type of large telescopes. And in the last image, you can see Kitt Peak National Observatory, or we call it as KPNO, and it is located in the United States. So the importance of these large telescopes, actually we use the data from these telescopes for our research. Actually, I'm also using data from the KPNO telescope for my research as well. And it can also be used to discover new planets like exoplanets. And we can observe explosive phenomena like supernovas using these type of large telescopes. So here I'm going to talk about some telescope stats. I think this is very important. Before using an optical telescope, you need to know these things. At least you have to have a slight idea about these things before using a telescope. So the first one is aperture. I think I explained that already. So an aperture is the diameter of the lens or the mirror that used to collect light. So basically, it's the diameter of the primary mirror or the lens. And then we have the focal length. I think this is a very basic concept. We all know what focal length is. So it's the distance between the primary mirror or lens to the focal point of that mirror or lens. And then the focal ratio is the ratio of the focal length to the aperture. And the field of view, I think I explained that also. The field of view is the circle of the sky, what we see through the telescope. When using a finder scope, as I mentioned earlier, we can see a bigger field of view, but through the telescope, it gets narrowed down, and so we can see, we cannot see a bigger field of view through the telescope. And I'll discuss about this resolving power and magnification in the upcoming slides in detail. So this is something very important, the light gathering power, especially if you are going to buy a telescope for yourself. This is something that you need to consider. You have to give your priority to this factor. So light gathering power is the ability of a telescope to gather the light or collect light. So it is proportional to the area of the aperture. As you can see in this simple formula, if we take D as the diameter of the aperture, we can find the area of the aperture using this formula. And then we know that the area is going to be proportional to the light gathering power. So here I have given an example. So let's take a refractor telescope. So if it has a 2-inch aperture, then if we substitute that in this equation, we get 4 times larger light gathering power because it's proportional to the aperture size. So actually here's a comparison. We have to compare that with the 4-inch aperture, with the 1-inch aperture. So if we substitute 1 inch, what happens is we can compare these 2-inch and 1-inch, and we can see that the 2-inch aperture has 4 times larger light gathering power. So then I'm going to talk about the resolving power, and this thing is also that something that you need to consider if you're going to buy a telescope. So the resolving power, I think I can explain this thing in using an example. So if we take a branch of leaves, and if we place that in front of our eyes, like we can count how many leaves are there, right? But if the same branch is in a tree, is still connected to a tree that is far away, we cannot identify, like we cannot count how many leaves are there, right? So when it comes to celestial objects, they are much further away than tree leaves, right? So we cannot sometimes distinguish objects when they are closely located together. So in this first image, you can see how this resolution works. So here you can see an unresolved image, but still there are two objects closely located together, but sometimes we cannot see in our naked eye. So in this real image, you can see how there are two stars are closely located together, but with our naked eye, we cannot see that. Like we see it as a single star. But there are things called double star systems. So in double star systems, two stars are closely located together. And when we see with our naked eye, we see it as a single star. But when we are using a telescope, we can clearly see that there are two stars. So here we can see how to calculate the resolving power. So there's a formula called Rayleigh's criterion. So with this, we can find the angular separation actually. So if we take the angular separation as delta theta, it is equal to the 1.22 times the lambda over d. So we take lambda as the wavelength of light and d as the diameter of the aperture. And when we find the angular separation, we can find the resolving power, because resolving power is the inverse value of the angular separation. So here we can see an example. So here I have directly substituted the value of 1.22 times lambda as 138. And it's given that the aperture size is 200 millimeters. So when we substitute these values, we get delta theta as 0.69 arc seconds using this formula. And then we are going to talk about the magnification. Usually people are more concerned about the magnification when it comes to buying a telescope. But actually, if we compare among these three factors, the resolving power, light gathering power, and the magnification, magnification is the factor that we should consider at last. Because no matter how much we magnify a celestial object, if we cannot see the details, if we cannot resolve them, I think we cannot use them in our research. So it's really important to be concerned about the resolving power and the light gathering power than magnification. So if you talk about the magnification, we can find the magnification of the telescope using this formula. So the magnification is equal to the focal length of the objective lens to the divided by the focal length of the eyepiece. So we can change the magnify using by changing the eyepiece focal length, but there's a limit actually. We cannot get a super high magnification by just reducing the focal length of the eyepiece. There's a limit to that. So we discussed a lot of theoretical things so far, and now I'm going to share a little bit about the observations with my experience. So the largest telescope that we have in Sri Lanka is located in Arthur C. Clarke Institute. So as you can see, this is a Cassegrain type telescope, and it has a 45 centimeter aperture, which is roughly about 18 inches. So I'll play this video. So recently, if you remember, there was an important astronomical event which was called the lunar occultation of Saturn. So this was our setting. It was a public event. We opened that event to the public, and this is where that event took place. So these are some images from that astronomical event. So you can see how the moon, how the Saturn hides behind the moon, and after some time, how it came back from the other side. And these are some images from a solar observation that we did also at Arthur C. Clarke Institute. So in this image, you can see this is not the color that you see the sun, right? So this image looks this color because we're using filters when we're observing the sun. We cannot directly look at the sun, or if we look at the sun using a telescope, we get blind. So we have to use filters. And in this filter, you can clearly see the sun spots. So this is an H-alpha filter. So you can see the sunspots, and you can, if you look closely into this image, you can see solar flares as well. So these are some images from the observations that we did at the University of Ruhuna. So in this image, you can see this is an image took using a white filter. You can clearly see the solar flares. So this is an image of the sun. You can clearly see the solar flares in this image. So this is an observation that we did with Dr. Henry from NASA. And this is an image of the sun that we took on that day. Sorry, the moon that we took on that day. So these are the two main telescopes that we use for our observations in University of Ruhuna. So these are some of the images that we took from our last observation. So in the first image, you can see Jupiter and the Galilean moons. And in the second image, you can see the Orion constellation. So that's all I was planning to discuss with you all in this session. So I think we can move to the question round, right? I think there are some questions in the chat box. Shall I proceed with answering them?
Yes. We will now open the floor for a brief 10-minute Q&A session. So please feel free to unmute your microphones and ask any questions you may have for Ms. Vishali.
I think there are some questions in the chat box. Shall I start by answering those questions?
Okay.
Okay. What's the use of red dot finder? Somebody has asked. So I'll go back to that slide. Yes. So a red dot finder is also a finder scope. So the difference is we are using a laser pointer here so that we can point to the celestial object, to the specific object that we are looking at. That's the only difference. It's also a finder scope. We are using it to see, to point to a celestial object, because through the telescope, we cannot sometimes figure out where we are looking at. So we get the help of a finder scope in that case. So there's another question, why we didn't use silver coating instead of gold in James Webb Space Telescope. Right. So the answer to this question is it's not an optical scope. It's built that way as an infrared telescope. So they want to detect the IR rays or the heat basically that comes from celestial objects. So that's why they have coated gold instead of silver. In the telescopes that like in our university also we fabricate telescope mirrors. In that case, we use aluminium, but sometimes we can use silver as well. But aluminium and silver we use for optical telescopes. But if you're building an infrared or near infrared telescope, we have to use gold coating. And there's another question. How we can clean our telescope lenses. So for cleaning the telescope lenses, there's something called optical tissues, and the optical tissues, and we have to use the deionized water. So using those two, we can clean the telescope lenses. I think there's another question. Silver can reflect infrared waves. No. When we're using silver, it's for the optical telescopes. If we want to build an infrared telescope, we have to use gold coating. I think I answered all the questions. I think they don't have any more questions, right?
On behalf of SEDS Mora and everyone present, I'd like to extend our sincere gratitude to Ms. Vishadi Liyanage for taking the time to join us today, especially considering her busy schedule. Your insightful and captivating lecture was truly enlightening, and we deeply appreciate the wealth of knowledge you shared with us. We would also like to extend our sincere gratitude to Mr. Kanishka Samararatne for his kind recommendation, which made today's insightful session possible. I hope all of you found this session as inspiring and rewarding as I did, and that you gain new perspective from today's discussion. So, with that, we wrap up the third session of the Cosmic Chronicles webinar series. Thank you all for being with us today, and we at SEDS Mora are excited to welcome you to our upcoming sessions as well. Have a great evening, you all.
Thank you very much.